Hey there, and welcome to Rules and Simplification. We're going to review some of the rules and the simplification procedures that you're going to be using in the rest of your algebra life. We'll start with a review of the exponents. Now remember what an exponent is when you have x to the third power. What does that mean? That means we have x timesing itself 3 times. This is exponential notation. This is expanded notation. And when you take a number, 2 to the third power, and make it an 8, then that is evaluated. Let's look at some of those rules. So first of all, what happens when you take, say, x squared times x to the 7th power? If you remember the rule, you're going to add these exponents. But why? Why do we do it? Well, this one says we got 2 x's. This one says we got 1, 2, 3, 4, 5, 6, 7 of them. And 2 and 7 now timesing all together, we now have 9 of them. So that's the first rule. Multiplication will give you addition of exponents. So if we take something, say, like x squared to the 5th power, here's the next rule. So we have a power to a power. A lot of power going on there. So we have, do you remember that rule? This is when you multiply them to get x to the 10th. But let's go slow motion and see why that's the case. We have x squared times x squared times x squared times x squared times x squared. And using this first rule up here, we're going to add that up. 2 plus 2 plus 2 plus 2 plus 2, which is 5 times 2 gives us x to the 10th. Excellent. So there's the multiplication rule. There's the power rule. Now, if we look at this one right here, and we go the other way, say x to the 7th over x squared. Now, if multiplication led to addition of exponents, this is going to lead to, division is going to lead to subtraction. We're going to get an x to the 5th out of that, but let's do slow motion again. We have 7 x's. Now they're all timesing each other on top. 1, 2, 3, 4, 5, 6, 7 of them. And we're dividing it by 2 of them timesing together down on the bottom. That cancels with that. And look at that. 1, 2, 3, 4, 5. Oh, did I count too many of them? I did indeed. Let's get rid of that guy. Now we have x to the 7th over x squared. And yeah, we got 5 of them right there. So division leads to subtraction of exponents. Now notice what happens if I now do x squared over x to the 7th. Well, anytime you subtract numbers, you might end up with a negative. So let's slow motion see what this negative exponent means. It doesn't really mean you're timesing x by itself negative 5 times, but if you recall, the negative exponent means other direction. What's the other direction from timesing by itself? That's division. Let's look at it in slow motion, see what happens. Here we have x squared over 1, 2, 3, 4, 5, 6, 7 of them. And they cancel. Now when you cancel something, it always is dividing to 1. So this is the same as 1 over x to the 5th. And based on this rule, look at this. We now have a reminder that a negative exponent, all it does is flip. That's important to note. So that if we have, like, let's say 2 to the negative 3rd power, that is 1 over 2 cubed. It does not become a negative 8 or a negative number at all, but becomes a fraction, which would be 1/8. Interesting side note on this, if you have a negative on the bottom, let's look at that. That would be 1 over x to the 5th. Now when we divide exponents, we divide fractions, we multiply by the reciprocal, which in this case would be 1 times x to the 5th over 1 equals x to the 5th. So if you have a negative exponent on the bottom, it flips it up to the top. If you have a negative exponent on the top, it will flip it to the bottom. So things are considered simplified when the negative exponents are all gone and you've moved it up or down where it needs to go. A couple more rules. You'll see this thing, x to the 0 equals, and you're like, I don't know, what does it equal? Well, if we pull out a calculator really quick and do something like that, 5 to the 0 power, what do we get there? 1. How about 17 to the 0 power? It's 1 again. That's kind of crazy. So we have that anything to the 0 power will be a 1. How does that work? Well, let's go back to the division rule right here, which is something like if we had x to the 7th over x squared, we'd get x to the 5th. What if we have x to the 7th over x to the 7th? This rule says that we would have to have x to the 7 minus 7 gives us 0. But what's anything over itself? 1. That's right. So a 0 exponent means we have divided off all of the powers that we were multiplying by. So that's where we will always get anything to the 0 power is 1. And then, of course, the final and last one is anything to the first power is itself, because you're just timesing it by itself just one time. So that gives us a few review problems to look at on what these rules are. Let's do one where we have to put them together. If you had something like 2x to the 7th times 3x to the 5th, this is just straight multiplication, so you're going to get 6x to the, what's that rule? Add them together, 12th. That's right. How about if we had 3a squared b to the 5th over 5a to the 7th b squared? So this right here, when we simplify it, we actually have three problems. We have 3 over 5. This guy right here, look at what we have. We have a squared over a to the 7th. 2 minus 7 would be a negative 5, and then it would flip down to the bottom. Notice we can use the subtraction rule going the other way. 7 minus 2 would be 5 with the bottom guy winning. That will be a good shortcut that you'll be able to use. And here we have the b's, b to the 5th over b squared, and we get b to the 3rd power. So we simplify it like that. To the boards! So now we're going to pause the video and look at these problems. Go ahead and hit pause and try these, and then we'll work them out right here. Welcome back. So you've tried them, and now let's see what we get. We should have a 6x to the 5th. That's using the multiplication rule and adding the exponents. Notice the 2 and this 2 and this 3 multiply to 6, but the exponents will add. On the other one, 5 times 3 is 15. X to the, what is 7 plus a negative 4? That is a 3, 15x cubed. Ooh, look at this ugly big one here. This is going to take us a little bit of space. This negative 3 power goes to everything. Let's do that piece at a time. 2 to the negative 3, x to the negative 9. Notice we're taking a power to a power, which means we are multiplying them. So when this goes to everything in here, when it hits an exponent, it will multiply it. And y to the negative 12 over 3 to the negative 3, x to the positive 15, and y to the negative 27. So let's move all the negative exponents. So that guy's going to go down. So we're going to have a 2 to the 3rd on the bottom. That guy's going to go up 3 to the 3rd. The x to the 15 stays down there, but the x to the negative 9 will shoot down to the bottom. X to the 9th down there, and then that y is going to shoot up to the top as 27, and the y to the negative 12 will be down on the bottom with a positive exponent. So now let's simplify them. 3 to the 3rd power is 27. 2 to the 3rd power is an 8. Though that can't reduce. The x's right down here end up being x to the, they're multiplying, so we're adding exponents. That'll be a 24. Then we have a y to the 27th on top and a y to the 12th on the bottom. We will subtract exponents, so we will get a y to the 15th on the top. And there, it is simplified as much as we can. Okay, a little easier one, but sometimes a little bit complicated. This guy, we could do it one of two ways. So we'll do it up here. We could have p to the negative 5 minus 7 equals p to the negative 12 equals 1 over p to the 12th. That's one way to do it. The other way to do it is to take this guy and flip him down. Negative exponents flip. So we get 1 over p to the 5th, and that p to the 7th stays on the bottom. Now we're multiplying them. So those exponents add 1 over p to the 12th. Nice job. Okay, let's resume. The next topic in this video is order and swapping and identities and inverses. So let's look at something that's kind of important. We learned about the order of operations, that multiplication and division always have to happen before addition and subtraction. But you kind of did, left to right with addition and subtraction. Does it really matter if you go left to right or right to left when you're adding up a bunch of different numbers? Well, you can actually swap order in specific cases. And let's look at and see when we can do that. So, swapping order. So like 5 plus 3, is that always the same as 3 plus 5? Of course it is. Yeah, what about 7 plus 11 and 11 plus 7? Yeah, you can actually swap the order. This is called commuting something, C-O-M-M-U-T. So the commutative property, yeah, you can swap things places, this swap order. And that's kind of important, especially when you realize when you are adding things, let's say right here, you can add it. You can do this all the time. And you can do this specifically with all numbers. All numbers, which means variables. If I have an x plus a y, that will be the same as a y plus an x. And there's no distinction there. We're going to use this a lot. When you're adding things, you can move them around any order at all. Now let's look. Can you do it with multiplication? 5 times 3, is that the same as 3 times 5? Yes, it is. What about 7 times 11 and 11 times 7? Are those equal? Sure. And yes, this is true for all numbers. X times y is going to be a yx, and it doesn't make any difference which order you go in. What about some of the other operations? Subtraction? 5 minus 3 and 3 minus 5. Can you switch something around a subtraction sign? No, you cannot swap them. So subtraction does not have a commutative property. Now you should note that if I did 5 minus 3, I could switch it if I viewed this not as a subtraction problem, but use this subtraction sign as a negative 3, and that is a positive 5. Now I've kind of made it an addition of a positive and a negative number, which you can switch around anytime, which is actually the reason why you may have rewritten this as 5 plus a negative 3, because once it's an addition problem, you can switch around any order at all. That's kind of cool. So subtraction's out, you can't do it. Same thing with division. If you took 20 divided by 4 and 4 divided by 20, are those the same? No, they're not. Now note with multiplication, you can take 20 divided by 4, which is the same as 20 times 1/4. Oh, look at that. Division is the same as multiplication by reciprocal, which you can now switch around as much as you want to. How about exponents? Can we do some switching with exponents? So if we took 2 to the third power, is that the same as 3 to the second power? It's 8 equals a 9. No, does not work. So subtraction, division, and exponents, those operations, you can't do it. So really, these two are the ones. If you're only with addition, you can swap it, and it's called the commutative property. That's very important because it works with all numbers and any letters that are representing numbers as well. Variables, cool. So that's the commutative property. Now let's look at the associative property. If we had 3 piles of Skittles when we were in kindergarten, like a 2, and we had 3, and we had 4, and you add them up, if you put 2 of those piles together, the 2 and the 3, and then added the 4, that's the exact same thing as having 2 plus 3 plus 4 with that. Now, when we did order of operations, it was very important where we put the parentheses. We are now seeing that sometimes, specifically with addition, it doesn't matter where the parentheses go. 5 plus 9 is the same as 2 plus 7. And so it works with all variables as well. 2x plus 5 plus 3p. If it became valuable, you could write it as 2x plus 5 plus 3p and move that parentheses over there. That's called the associative property, or the ability to move parentheses. Let's see if multiplication does that. How about 2 times 3 times 5? Can you do it like that? Yep. What about 2 times 3 times 5? Does it really matter which order? It doesn't. So again, addition, wow, that's a happy, nice thing there. Addition and multiplication both have these properties that you can do them in any order. So if you see subtraction or division or exponents, if you can turn them into these kind of problem, yeah, by adding the negative, you'll get an addition problem. Dividing, yeah, you can actually turn them into multiplication problems, and they get these cool properties where you can swap things around or move parentheses. Let's 2x times p times L. Oh yeah, look at that. You could write it as 2 times x times p times L like that. Move the parentheses over there. Or 2xp, You put the parentheses there and it would still be the same. It, again, does not work with subtraction, does not work with division, and it won't work with exponents either. So we're going to stick with these two properties. That's crucial, these properties, to be able to identify what's going on. We get to rearrange things all over the place, and they will help us simplify things. So now let's look at the identity. So the identity, this thing is the invisible number. Let's write that out and then explain it a little bit. If I take 6 plus 0, well, I get 6. If I take 17 plus 0, I get 17. This number right here is useless with addition. Of course, when you were learning your addition facts, this was the best one in the world. You went home to your mom and you're like, Mom, go ahead, test me on my 0 addition facts. She's like, what's 7 plus 0? You said 7. What's 18 plus 0? 18. And then you said, no, give me a harder one. She's like, okay, what's 3,281 plus? Oh, 3,281. Yeah, this number is so cool. It's because it allows 6 to maintain its identity. It's the invisible one. You're like, well, why would we use it? I'll get to that in just a moment. So here, in multiplication, what is the identity in multiplication that allows a number to not change? And that is 6 times 1. Yeah, 17 times 1. That's right. This guy is the multiplicative identity, and that guy is the additive identity. You're like, well, what in the world are they good for? Well, we often will run into things that cancel each other out. We call them inverses. So these are, in addition and subtraction, we call them opposites. So like 2 plus a negative 2, or 2 minus 2, we get 0. When it becomes the invisible number, that's where we say, oh, these guys canceled. What we really mean is they added to the additive identity, which is now invisible in the problem. Don't ever say that at home, but that's what you're actually meaning. And it works with all numbers. So if you had 5x and you had a negative 5x and you add those two things together, it goes away, it cancels. Now with multiplication, it's a little bit different. You have to take 6 times a number to equal 1. And what's that number? We call it a reciprocal. And when you're using the reciprocal, it's like dividing, just like we did up here. 20 divided by 4 is the same as 20 times. It's the reciprocal of 4, or the multiplicative inverse. If you took 2/3, you'd have to times it by its reciprocal, which is 3/2. And you'll notice we get 6 over 6, which is 1. And we've actually done something like this before, where you would see this. If you had something, like simplifying, where you're like 6/8. In slow motion, the simplifying of this looks like, oh, that's 2 times 3, and that's 2 times 4. And notice what this 2 and this 2, when we say they cancel, it's actually 2 divided by 2, or 2 times 1/2, and that divides off to, oh yeah, look at that, that's a 1. And so we say it cancels because it now becomes a 1, which is the identity, and leaves you with 3/4. So these are the official names for the rules that go behind all the scenes with mathematics. Okay, let's pause the video. To the boards! So here are 7 problems where you are being asked to identify the property that has been enacted to say that these two are exactly equal. Go ahead and pause the video right now, and when you've listed out the properties you think they are, go ahead and turn it back on and let's check it. They swapped places. Yeah, swapping order, that is the commutative. Commutative property of, they swapped around a plus sign, so commutative property of addition. Number 2, what happened here? 3 plus 7p plus 5p equals 3 plus 7p plus 5p. They did not swap order, but the parentheses moved. So that is the associative property of addition. Number 3, 5 times 1/5 equals 1. What is going on? These two are canceling each other out to the invisible identity number. So they are inverses, multiplicative inverses, also known as reciprocals. Number 4, what's going on here? The negative 3x and the positive 3x undo each other and become the invisible number in addition. So these guys are canceling, or they are opposites of each other. So they are additive inverses. Number 5, 7m plus 0 is 7m. The 7m is maintaining its identity by being added to nothing. So that is the additive identity. Number 6, 2 parentheses 3 plus 5x equals parentheses 3 plus 5x times 2. Ooh, what's going on here? Did the parentheses move? Not really. They're still around the 3 plus 5x. So what changed? This number 2 and this number 3 plus 5x, all as one group, switched places. So they swapped. That means it is commutative. Commutative swaps orders. And they swapped around. These guys are timesing each other. So this is a commutative property of multiplication. Oh, that was a little tougher, seeing those parentheses in there. Number 7, what's happening here? 5 times 3x times 5p, 5 times 3x times 5p. No swapping of order, so it cannot be commutative. But what does happen is that these parentheses just move. So that is the associative of multiplication. And there you have it. Let's resume with the final one. And finally, we get to simplifying. Now, all the rules that we've covered so far with exponents and the commutative property and the associative property and identities and inverses all will go to simplifying. A couple of foundational concepts here. You always need to add like terms. So if you don't have like terms, you can't do it. So 2 penguins plus 3 penguins, well, these are like terms. You're going to end up with 5 penguins. That's nice. It makes it simpler to see that rather than this. However, if you have 2 penguins plus 3 sheep, you're stuck there. 2 penguins plus 3 sheep. You're not going anywhere. That's as simple as it possibly can get. So a couple of rules that will help with the simplifying. There is often a problem that creeps up with adding like terms. And that is when I have something like 2 parentheses p plus 5 plus 7 times 4p minus 3. Let's do something like that. Notice that this p and this 5, we don't know what it is, so we can't add these together. This doesn't become 5p. These are unlike terms, so you can't add them. Well, here's a p over here, but he can't get there because of order of operations. He's stuck in the parentheses. This is what is known as the distributive property. And this is probably the most important thing you will ever see in math, and will carry through all of your courses. This can be jumped in to there, 2p plus 10. This guy can be jumped in, include this sign with it, and you get plus 28p minus 21. Now, officially it says a, b plus c, so this is with variables, so this works for all numbers, equals ab plus ac. Yeah, that's important, that this outside the parentheses can distribute in there. So now look what happened. Without the parentheses, we are free to combine like terms. Technically, you would commute the 10 and the 28p. You'd switch them places, but you won't have to write out all of that stuff. You'll just have to say, oh, there's actually 30p, and then the numbers are, oh, look, minus 11. And we've made it just as simple as possible. Math teachers have gone to great lengths to make these problems look incredibly complex and laborious. So part of your job is to be able to simplify it down into some of the nicest stuff you have. In fact, this has a great gospel connection to it. Let's look at a quote here. This is from President John Taylor. It is true intelligence for a man to take a subject that is mysterious and great in itself, just like mathematics, and to unfold it and simplify it so that a child can understand it. What a great description of what intelligence really is to boil down through all the complexities down to the very essentials of what it takes. There's also a great description of this by President Uchtdorf. Let's listen to what he says about simplifying down.
Are we making our discipleship too complicated? This beautiful gospel is so simple a child can grasp it, yet so profound and complex that it will take a lifetime, even an eternity, of study and discovery to fully understand it. But sometimes we take the beautiful lily of God's truth and gild it with layers upon layers of man-made good ideas, programs, and expectations. Each one by itself might be helpful and appropriate for a certain time and circumstance. But when they are laid on top of each other, they can create a mountain of sediment that becomes so thick and heavy that we risk losing sight of that precious flower we once loved so dearly.
Those are some powerful words. And in math, though with not as deeply spiritual of consequences, we do the exact same thing. We boil something that looks ugly and nasty down into its very essentials so that we can work with it. We do it with fractions, we do it with expressions, we'll do it whenever we have parentheses, and we'll use that throughout the rest of the semester. One more comment before I let you loose on some more to the board's problems. Notice that this equals sign means you can go either way. If I had something like 7x plus 14, you actually, if it was necessary or if it was useful to you, you could go backwards and say, hey, you could pull a 7 out of both of these and get an x plus 2. When you go this way, it's called distributive. When you go from there to there, you are undoing that multiplication, which we learned earlier was called factoring. So factoring works with these expressions with 2 terms in them, or 3 terms, or 4 terms if we wanted to, and that's factoring. Okay, let's look at some boards problems. Here are some problems, number 1, 2, 3, and 4, that look incredibly ugly, and your job is to simplify them. So pause the video, give them a shot, go to the boards, and unpause the video and start playing again when you're ready. Welcome back. So this one, there are no parentheses to get rid of. We just need to combine the x's together. There we go. We got 5 x's. How many y's do we have? Positive 5 and a negative 9. So that's minus 4y and plus 8. And that's as combined as we can get it. That is simple, just like a child can understand. Number 2. Ooh, this one looks bad. Yeah, we got parentheses all over the place. So let's distribute. So we get 3x minus 15y. Over here we get minus 7x minus 28 and then plus 5y. Alrighty, let's combine like terms. We have a 3x and a minus 7x and we get negative 4x. Minus 15y plus 5y, that's minus 10y. And then this guy's all by himself right here, minus 28. Be sure you keep those signs with it. Now some of you may have the question, what if we wrote it a little bit differently and had negative 28 first and then minus 10y and minus 4x? The question is that the same thing? Well, yes, the commutative property of addition allows you to take that negative 28 and put it here or here. You can move it any order you want to and rewrite those terms because they're being added if you keep these minus signs with them. Good. Number 3. This has got bigger brackets. So let's start from the inside and put this in here and get rid of the parentheses. So we have 2 bracket 5 plus 3. Let's go ahead and multiply that guy in and we get 6x minus 21 plus 4x. And we could combine right now. This 6x and this 4x could make a 10x, and 5 and minus 21 minus 16 if we wanted. Or we could distribute right now just like that. So we get 10 plus 12x minus 42 plus 8x. Okay, how many x's do we have? 12x and 8x, that gives us 20x. And 10 minus 42 is a minus 32. So you could write it this way or you could write it this way, and both of them are absolutely correct. All right, last one, number 4. We have braces brackets, and parentheses. They all provide the exact same function of grouping things together, but that's the only difference is how they look. So let's start with the parentheses in here and jump that through. So we get 2 brace 3m minus bracket 5x plus 10 plus 3, close that bracket, plus the 4x, close the brace, minus 7m. Ooh, okay, can we get rid of this bracket? Yeah, this negative sign, think of it as a -1, just distributes through there because you're subtracting the whole thing in the bracket, and we get 2 brace 3m minus 5x minus 10 minus 3 plus 4x minus 7m. Excellent. Let's see if we can put anything together in here. Yeah, the minus 5x and plus 4x will combine. We can do that after we distribute the 2 in. So we get 6m minus 10x minus 20 minus 6 plus 8x and then minus 7m. Do you see how we're able to take off the parentheses, then the brackets, and then the braces? All right, so 6m minus 7m, that's a -m. The x's, there's negative 10x and plus 8x, that's minus 2x. And then minus 20 and minus 6, that's a minus 26. Let's put boxes around those so we can see what two terms we put together. So you can write it like this, or in any other order. -26 minus m minus 2x would also be fine. All right, nice job. And that will conclude this particular lesson.